everybody, Mr. Judson here. So last Friday or Thursday we did this problem right here and we tried to figure out what that exponent was. And I think it was something like 2.631, something like that if I remember right. And I told you we would learn another way to be able to do that. So I'm going to show you something here. Remember I told you when we talked about logs last week, I said logs are exponents and you have to force yourself to think like an exponent. So if I say 3 raised to what power equals 18, that's really like me saying log base 3 of 18 equals what? 3 raised to what power equals 18? I'm looking for an exponent. Okay? And one of the things that we want to talk about today, I still can't figure this out because our calculators don't operate in base 3. They operate in base 10. So we can't do this. Okay? However, one thing that has been developed is something called the change of base formula. Okay? And when we say change of base, what we're doing is we're trying to change this to a base 10 problem. So our calculators can do it. So the log base b of some number, I'll just call it n, is equal to log of n over log of b. And remember, I told you guys if we don't write the base in here, it's understood to be base 10, right? So what I've done is I've changed this from a base 3 problem now to a base 10 problem. And then all of a sudden my calculator can do this, right? Now, interestingly enough, it doesn't matter if you use a log or a natural log. Okay? Both of those will give you the same answer, and I'll show that to you here in just a second. So I don't know if you guys remember this, but I kind of moved my calculator off to the side on Thursday or Friday and said, I'm going to figure out the answer real quick. Well, this is what I did. I said, this right here has to equal log 18 divided by log 3. I did the change of base formula. And I want to make sure we notice this because this 3 is a subscript, but it's not a subscript here. It's, everything's written on the same level. Same thing up here. It's log base 10 of 3 and log base 10 of 18. I just don't have to write the 10 in there because it's just understood to be that if it's not written. Okay? And so then if I grabbed a calculator and I said, let's do log 18 divided by log 3, and that's what I did during class, 2.631. So 3 raised to that power gives me an answer that's pretty close to 18. Now, let's just double check and see if this also works. If I do the natural log, so the natural log of 18 divided by the natural log of 3, that also produces that exact same answer. So you can see one of them here, here's the other. Digit for digit, they're all the same, all the way across. Okay? So this is called the change of base formula. That'd be a good thing for our note card, right? Okay, those kind of things can go on the note card. So if I asked you guys a question like this, 5 raised to the x power. Now if I put something like 25, we'd all get that right, okay? But if I put something like this, now, let's be careful. I know right now a lot of you guys are thinking 8, right? But think about that. 5 times 5 is 25, times 5 is 125, times 5 is 625. I'm way past 40, and I haven't even gotten to 8 yet. Okay? So be careful. A lot of people look at these and they go, oh yeah, 5 times 8 equals 20, but that's not what we're saying. 5 raised to what power equals 40? Did I say 20? I don't know. Let's see if you can figure that answer out. All right, so I would look at this and say, well, 5 raised to what power equals 40? This is exponential form. I'm going to change it back to log form. So log base 5 of some number equals the exponent, which that some number would be 40. And now we're saying 5 raised to what exponent equals 40. And so to do this, I need to do the change of base formula. So I'm going to say this is log of 40 divided by log of 5. And let's see what we get. So log 40 divided by log 5. 2.292. So 5 raised to the 2.292 should give us an answer close to 40. This is rounded, so I don't expect to get exactly 40, but it should be close. Let's just check it real quick. 5 raised to the 2.292. And I hit enter. Yeah, I got an answer pretty close to 40. Okay. All right, so that's one thing we'll see for today is the change of base formula. The other thing that we're going to see is what's called the properties of logs. All right, so the properties of logs, there are 3 of them, okay? And again, if there was ever a time where you have to think this way, this is it. You know, when I told you, when we talk about logs, you have to think like an exponent. All right? Here's what I mean. First property. If I'm going to do log base b of u times v, then this is equal to log base b of u plus log base b of v. Okay? Now what does this mean? You know, I look at this and what I see is I'm multiplying with exponents. So let's go over here and write something down. If I've got x to the 5th times x to the 8th, I'm multiplying with exponents. So what do I do with those exponents? Well, the rule is you add them and you get x to the 13th power, right? So if I'm multiplying with exponents, then I have to add those exponents. Right? You see that? We're trying to think like exponents. Here's the next property. Oops. If I've got log base b, and when I say base b, that means this can be log base 3, log base 7, I don't care what it is, log base 10. Log base b of u divided by v. Well, now I'm dividing with exponents. Right? Dividing with exponents. So what if I had something like this? X to the 8th, let's see, that was 13, over x to the 5th. What would I do with those 2 exponents to get my answer? I would subtract them, right? So I would get x to the 3rd. So if I'm dividing with exponents, that means I should subtract them. So I get log base b of u minus log base b of v. When I divide with exponents, like we are here, we did 8 minus 5 to get the 3. So when I divide with exponents, I need to subtract those. All right, we got one left. Log base b of u raised to the n power. So what I see here now is I see an exponent raised to an exponent. Remember, logs are exponents, so I got to think that way. Exponent raised to an exponent. What do we do if we've got x to the 5th power and I raise that to another exponent? What am I supposed to do with those exponents? Well, we're supposed to multiply them, right? So I would get x to the 20th power. So what do I do when I raise an exponent to an exponent? I multiply them. And the way I'm going to write that is I'm going to say, let's bring that n down in front. And it was an exponent here, so it's still an exponent there. And we know logs are exponents. So an exponent raised to an exponent, we multiply those two exponents. Now, most of the time what we're going to say is that if you've got a log of something raised to an exponent, you just bring that n down in front and write it there. But that's the reason why, is because when you raise an exponent to an exponent, you multiply those things. All right? So there it is. There's our three properties for logs. Now, these three things also apply to natural logs, because it doesn't matter what the base is. This can be base 2, base 5, base 7, base e, right? 'Cause remember, log base e is a natural log. So everything that I just wrote down here, right here, is also true with natural logs. So if I had a natural log of u times v, then that would equal natural log of u plus natural log of v. If I'm going to multiply with exponents, I have to add them. If I've got natural log of u divided by v, well then I'm dividing with exponents, I need to subtract those. So natural log of u minus natural log of v. Always the one on top minus the one on the bottom. Remember that rule that when you have negative exponents, move it down into the denominator? Negative exponents go into the denominator. So that v has to be the negative exponent. All right, this last one, if I've got a natural log of u raised to the n power, I'm raising an exponent to an exponent, and so I need to multiply those. So I'll bring the n down in front, and I'll multiply it times natural log of u. All right, so these three properties that work with common logs, they also work with natural logs, because the base doesn't matter. Right? This just means base e over here, this is everything else. So what they're going to ask us to do is they're going to ask us to either expand or condense expressions. What I just did right here is this got bigger, right? So I'm expanding if I go this way. If I go back this direction, I'm condensing it into something that's smaller. Okay, so that's really what our goal is with these properties for right now, is to expand and condense them, just to help us understand what's happening with exponents. Okay, I do want to say this. If I had to tell you guys which one of these properties is probably the most important, it's that one right there. That's the one that's going to help us solve equations where the variable is in the exponent. Okay? All right, let's expand and condense a few here. All right, so we'll do this first one together. It says natural log of 7 times e to the third. So right there, those are the two things that are being multiplied. So what I'm going to do is I'm going to say this is a natural log of 7 plus a natural log of e to the third. And so that's using our first rule, right? If you're multiplying with logs or with exponents, you have to add those exponents. Okay? If you're multiplying with exponents, you have to add them. But now we see something that looks like our third rule right here. If I have an exponent raised to an exponent, I want to bring that down in front so that I can multiply those. So this is going to equal natural log of 7 plus 3 natural log of e. There it is. Now, you might look in the book and not see this answer. I've expanded this, but some people would make the argument that this is not completely simplified. And I think I would agree with them, okay? There's something about natural log of e. Every time you see it, that should catch your attention, right? Because if I write down natural log of e, well, remember, natural log means log base e. So log base e of e, and then we're saying e raised to what power equals e? E raised to what power equals e? Well, this exponent's right here's a 1. This looks like our one-to-one property. Okay, my bases are the same, which means my exponents have to be equal. So what's this going to be? It's got to be 1. Right? E raised to what power equals E? This equals 1. So something that we should always keep track of is that the natural log of E equals 1. And what that means is if you stop here, you haven't really simplified this all the way. We know what that's equal to. It's kind of like someone who will stop and say the answer is 4 times 5. Well, why didn't you say 20? You haven't finished yet. If we say the answer is natural log of E, we haven't finished yet. We know what that's equal to. It's equal to 1. Okay? That could go on your note card. It's a definition. Something that's always true. Right? So when I see that right there, I go, oh, well, that's just 1. So really, this should equal natural log of 7 plus 3. There, I fully expanded that now. There's my answer. Okay? Let me give you guys one to try. All right, you guys try this one. I want you to completely expand that log expression. All right, so I am multiplying 3 things with exponents. It means I need to add all 3 of those exponents. So I'm going to say log base 8 of 2 plus log base 8 of a squared plus log base 8 of b cubed. Now, sometimes people say, can't you bring those numbers down in front right away, like 2 times 3 and get 6? Well, no, because 2 isn't being raised to an exponent. So if you put a 6 here, it means all of this is being raised to the 6th power. It's not. So we need to save that for the next step. Okay? So let's see. Now I've got log base 8 of 2 plus, I'm going to bring this 2 down in front. So 2 log base 8 of A. And I'll bring that 3 down in front, and I get 3 log base 8 of B. And there I have expanded this, but I have not finished. Anytime I see just numbers, that always catches my eye. And I'm always asking myself the question, could I go a little farther? Could I do something with that? Well, this right here means 8 raised to what power equals 2? Well, I know the cube root of 8 is 2. So how do you write the cube root as an exponent? So if you guys didn't know this, anytime you have a root, so I'm just going to call this n, of some number x, that equals x raised to the 1 over n. Okay? Whatever that index is for our radical, that just becomes the denominator here. So if you want to just check this real quick, we'll get our calculator here. I'm going to go math. I'm going to choose the cube root option here, option 4. I'm going to take the cube root of 8. We'll just stick with an easy number. Answer's 2, right? There it is. And now if I go 8 raised to the, I'll put my fraction inside parentheses, 1 divided by 3, okay, because 3 was the index up here, this should also give me the answer 2, right? Whatever the root is, that index goes in the denominator. So there's another thing for your note card. So 8 raised to what power equals 2? That would be 8 raised to the 1/3. Cube root of 8 is 2, so 8 to the 1/3 is 2. So this whole thing right here can be simplified down into 1/3 plus 2 log base 8 of A plus 3 log base 8 of B. This is a spot, you know, stuff like this and stuff like this, where I really feel like us being out last spring is going to affect our understanding of this here. I'm trying to go slow. I'm trying to make sure I explain everything and talk about this if we haven't seen it before. But I think for some that's going to be a bit of a struggle. Okay. All right, there's my answer. All right, so we want to expand this one. So again, here's a square root. I want to remember that doing a square root is the same as doing x raised to the 1 over whatever that root is. So if there's no index written here, it's meant to be 2. And so this whole thing right here really is the same as a natural log of x squared over 2y raised to the 1/2. And because everything here is raised to the 1/2, that means I can bring that 1/2 down in front. And so what I get is 1/2 natural log of x squared over 2y. Okay, I've got an exponent raised to an exponent, so I can bring that exponent down in front and multiply those two things. All right, you guys keep on going. We're still expanding, okay? We're not trying to figure out what this is equal to, because we can't. It's just a bunch of variables. We're just trying to expand it into a larger expression. All right, so and the other thing I got to be careful of here is, as I expand this, I got to remember it's 1/2 times everything that this becomes. So I've got 1/2 times a natural log of x squared minus, because we're dividing, a natural log of 2y. And then I'm going to distribute this 1/2 to each of those. So 1/2 natural log of x squared minus 1/2 natural log of 2y. And so now with this one, I've got an exponent raised to an exponent, so I can bring that 2 down in front. So I've got 1/2 times 2 times the natural log of x. Here I'm multiplying with exponents. And when you multiply with exponents, you're supposed to add those. So I've got a negative 1/2. This right here is turning into this. Natural log of 2 plus natural log of y. And I don't want all these parentheses in there. If I see parentheses, it means I still have something to do. I'm not finished yet. Right? So 1/2 times 2, that's just 2 over 2, which is 1. So I get natural log of x. I've got to distribute this negative 1/2 to each of those. So minus 1/2 natural log of 2 minus 1/2 natural log of y. And that is now expanded as far as it can go. I don't know, I kind of remember doing this when I was in school. It's a long time ago, it's getting harder to remember. But I remember kind of liking it because it's not real hard, but yet it still makes me think a little bit. And you get to the end and you check your answer in the back of the book, and if you got it right, it's like, good, I understand. So I always kind of like these, right? So let's try going the other direction. Let's try taking an expression like this and condensing it back into a single logarithm. All right, so we'll keep the first one kind of easy. They're saying to condense into a single logarithm. So common log or natural log, doesn't matter. I want to condense this down so I just have the natural log of something. All right, you guys go ahead and try it. All right, so first of all, I want to look at this and I want to think, okay, I need to bring that 2 back up. I'm also looking at this and I'm thinking that you subtract exponents when you're dividing. So when I condense this, I'm going to be dividing two things. But I want to take care of this first. So I've got natural log of x minus natural log of y squared. Okay, if we're condensing, anytime you have numbers in front, you got to bring them back up. We're undoing what we just did a little while ago. Now I look at this and say I'm subtracting with exponents. That happens with division. So I've got x over y squared. There it is. I've condensed this down to a single logarithm. How do you know you're down to a single logarithm? Well, because I only see one log function written there. And again, it doesn't matter if it's common log or natural log. It doesn't matter what the base is. Right? Let's try another one. All right, you guys go ahead and try it out. So when I do this, I want to think, back to the order of operations. You always do what's in parentheses first. That doesn't change. Okay, so I want to condense all this stuff first before I deal with that 1/2 that's out in front. Okay, I'm going to bring that 2 up just like I did over here. So this is going to be 1/2. Oops. So this is going to be 1/2 times log 4 plus log x plus log y squared. And now I'm adding all these exponents, which means we must be multiplying, because that's when you add your exponents together. So I've got 1/2 log of 4xy squared. Okay, when you multiply with logs, you add those. That's what we're doing here. We're adding these 3 things together. And so now I can bring this 1/2 back up above. It'll be the exponent for this. But if I do that, log of 4xy squared to the 1/2, that really means square root, right? An exponent of 1/2 means the square root of all this. So this really becomes the square root of 4xy squared. And I still don't think I'm done. And I say that because I look at this and I go, do I know what the square root of 4 is? Yeah, it's 2. Do I know what the square root of y squared is? Yeah, it's y. So what I have here is log of 2y root x. That's my simplified version. Now, this is almost correct. There's one slight problem with this, and it's this. Anytime you take a square root of a number, you're supposed to get a positive answer, all right? There's a difference between these 2 questions. X squared equals 4, so x equals what? Or what's the square root of 4? The answer to this is just 2. But over here, there's actually 2 numbers you can plug in to make this equation true. And so that's why when we've said we take the square root, you get plus or minus 2. So my answer to this would be plus or minus 2. The answer to a square root is not plus or minus whatever the square root of that number is. Okay? When you're just doing a square root, you have to get a positive answer. So when I look at this and I go, okay, I took the square root of y squared. Did I get a positive answer? Did I? And the question I ask myself is y positive or negative? I don't really know. What if it's negative? It means I just took a square root and got a negative answer. Can't do that. When you take a square root, you get a positive answer. So what we do is we put absolute value signs there. Log of 2 absolute value of y times the square root of x. Okay? On a year like this, I'm not too worried about that. But for those of you who really want to understand math and make sure you get it, that's probably something that's pretty important that'll come up later. I remember seeing this in my college classrooms all the time. I don't know what it is about college professors, but they like square roots. Or, I'm sorry, they like absolute values. Things always come up that have to do with an absolute value. All right? Let's try one more problem. All right, let's see if we can condense this one. All right, so, again, I've got a number here. I want to bring that up first. So I've got natural log of x minus natural log of x plus y squared. Now, do we have to go ahead and multiply this out and FOIL it? Where you square the first, multiply the 2 and double it, square the last. No, you don't have to do that for these. We can leave that as an exponent. Right? So I would look at this and say I'm subtracting with exponents. That happens with division. And so what I get is natural log of x divided by x plus y squared. Alright, there it is. I've condensed it. Alright, that's what we have for today, you guys. Expanding and condensing logs based on their properties. We've also got our change of base formula. And so let me get you guys a homework assignment. Alright? Alright, so we got assignment number 16. This is week 16. Today's Monday. We're going to do page 243. And what we're going to do is we're going to count by threes here. So 3, 6, 9, 12, and so on until we get to 72. This looks like a huge assignment. It's really not huge. Okay, a lot of these questions are, do this on your calculator. It's like, do 4 raised to the 2.37, you know. So you're just punching things into your calculator and getting answers fairly quick. Or use the change of base formula. That's a calculator problem. So it's going to go pretty quick. Some of these where they ask us to expand it, they're really simple, like natural log of x squared. Bring the 2 down in front, you're done. Okay? So a lot of these problems will go really fast. It's not as long of an assignment as it looks. Alright, that's it you guys. So take care, stay safe. I'll see you in a couple days.